One of the most astonishing results of special relativity is that mass and energy are equivalent, in the sense that a gain or loss of mass can be regarded equally well as a gain or loss of energy. Consider, for example, an object of mass m traveling at a speed v. Einstein showed that the relativistic total energy E of the moving object is related to its mass and speed by E equals mc squared divided by the square root of 1 minus v squared divided by c squared. To gain some understanding of this equation, consider the special case in which the object is at rest. When v equals 0 meters per second, the total energy is called the rest energy, E0, and this equation reduces to Einstein's now famous equation, E0 equals mc squared. The rest energy represents the energy equivalent of the mass of an object at rest. With the speed of light squared, as it appears in this equation, we can see even a small mass is equivalent to an enormous amount of energy. Consider a 0.046 kilogram golf ball lying on a green. If the rest energy of this ball were used to operate a 75-watt light bulb, how long would the bulb remain lit? We start by noting that the average power is the rest energy divided by the time, or P bar equals E0 divided by T, or T equals E0 divided by P bar, which equals mc squared divided by P bar. Plugging in the values gives 5.5 times 10 to the 13 seconds, which is 1.7 million years. When an object is accelerated from rest to a speed v, the object acquires kinetic energy in addition to its rest energy. The total energy E is the sum of the rest energy E0 and the kinetic energy Ke, or E equals E0 plus Ke. Therefore, the kinetic energy is the difference between the object's total energy and its rest energy. Using our equations for the relativistic total energy and the rest energy, we write Ke equals E minus E0, which equals mc squared divided by 1 minus v squared divided by c squared minus mc squared, which equals mc squared times 1 divided by the square root of 1 minus v squared divided by c squared minus 1. This reduces to the classical value of 1/2 mv squared when v is much less than c. Let's do a simple example. Suppose an electron is accelerated to a speed of 0.9995 c. Determine A, its rest energy, B, total energy, and C, kinetic energy. The rest energy is given by E0 equals mc squared. Plugging in the values for the speed of light and the mass of an electron, we have E0 equals 8.187 times 10 to the negative 14 joules. For part B, the total energy, we have E equals mc squared divided by the square root of 1 minus v squared divided by c squared. Plugging in the values gives E equals 2.59 times 10 to the negative 12 joules. Finally, the kinetic energy is given by the difference between the total and rest energies, giving Ke equals E minus E0 equals 2.59 times 10 to the negative 12 joules minus 8.187 times 10 to the minus 14 joules, which equals 2.51 times 10 to the negative 12 joules. It is useful to have an equation that relates the total relativistic energy to the relativistic momentum. Starting with the relativistic momentum, we rearrange to give P divided by V equals m divided by the square root of 1 minus v squared divided by c squared. The total energy is E equals mc squared divided by the square root of 1 minus v squared divided by c squared. Substituting for m divided by 1 minus v squared divided by c squared in this equation gives E equals pc squared divided by v, or v divided by c equals pc divided by e. Putting this back in for v divided by c, we obtain E equals mc squared divided by the square root of 1 minus p squared c squared divided by e squared. Finally, solving for e squared gives e squared equals p squared c squared plus m squared c to the fourth, which is our final relation between the relativistic momentum and energy. In summary, the relativity